Have you ever wondered about the importance of carbon and its compounds in our daily lives? Carbon, a non-metallic element, holds a unique place in the world of chemistry. Its ability to form covalent bonds and its allotropes make it incredibly versatile. This video will delve into these fascinating aspects, along with exploring the saturated and unsaturated compounds, chains, branches, rings, and more. We'll also touch on nomenclature, functional groups, and physical and chemical properties. With that brief introduction, let's dive deeper into the fascinating world of carbon compounds. Now, why is carbon so special? It all comes down to a type of chemical bond known as the covalent bond. Covalent bonds are formed when two atoms share electrons, allowing them to fill their outer electron shells and achieve stability. Carbon has 4 electrons in its outer shell and can form 4 covalent bonds. This makes carbon incredibly versatile as it can bond with a wide range of elements. Let's talk about the allotropes of carbon. These are different forms of carbon that exist due to the way its atoms are bonded together. The most well-known allotropes of carbon are diamond, graphite, and fullerene. Diamond is the hardest known mineral thanks to the strong covalent bonds between its carbon atoms. Graphite, on the other hand, has layers of carbon atoms that can slide over each other, making it soft and slippery. Fullerene has a unique structure that resembles a football, so thanks to covalent bonding, carbon can exist in different forms, each with its unique properties. Carbon's versatility is truly remarkable, isn't it? This small, unassuming atom is the backbone of an incredible diversity of compounds. This is primarily due to carbon's ability to form strong covalent bonds with other carbon atoms, resulting in chains, branches, and rings of varying complexity. Now let's talk about saturated and unsaturated compounds. Saturated compounds are those in which carbon atoms are linked by single bonds, allowing them to hold as many hydrogen atoms as possible. On the other hand, unsaturated compounds contain double or triple bonds between carbon atoms, meaning they can accommodate more atoms if the conditions are right. The structures of carbon compounds can be highly complex thanks to the chains, branches, and rings that carbon atoms can form. These structures are not just random, they follow specific rules and patterns, making the world of carbon compounds a fascinating and orderly universe to explore. As you can see, the versatility of carbon leads to an astounding variety of compounds. Moving on, let's explore the homologous series and functional groups. A homologous series is a family of organic compounds with a common general formula, and members of the same series show similar chemical properties. Each member differs from the next by a CH2 unit, and this regular pattern lends predictability to the series. For instance, in the alkane series with general formula CnH2n+2, methane, ethane, and propane are consecutive members. Now turning our attention to functional groups. These are specific groups of atoms within molecules that are responsible for the characteristic chemical reactions of those molecules. For instance, the alcohol functional group is an O group. This group defines the properties of alcohols such as ethanol. In a nutshell, homologous series and functional groups form the backbone of organic chemistry, providing a structured and systematic way to categorize and understand the vast array of carbon compounds. Homologous series and functional groups play a vital role in the classification and identification of carbon compounds. Now let's delve into the chemical properties of carbon compounds and their real-world applications. Carbon compounds exhibit a number of fascinating chemical properties. Let's start with combustion. When carbon compounds, particularly hydrocarbons, burn in the presence of oxygen, they release large amounts of heat and light, making them excellent fuels. Your car, for instance, runs on the combustion of gasoline, a mixture of hydrocarbons. Next is oxidation, where carbon compounds react with oxygen to produce new substances. Take ethanol, for instance. Its oxidation produces ethanoic acid, a key ingredient in vinegar. Speaking of ethanol and ethanoic acid, they have some intriguing properties of their own. Ethanol, a liquid at room temperature, is a good solvent and is used in beverages, medicines, and fuels. Ethanoic acid, on the other hand, is what gives vinegar its sour taste and is used in food preservation. Carbon compounds also undergo addition and substitution reactions. In addition reactions, unsaturated carbon compounds react with substances to become saturated. Substitution reactions, on the other hand, see one atom or group in a carbon compound replaced by another. Finally, let's talk about soaps and detergents, both of which are sodium or potassium salts of long-chain carboxylic acids. They work by forming micelles around grease particles, allowing them to be washed away with water. From the fuel in our cars to the soap in our bathrooms, carbon compounds are everywhere. Let's now take a closer look at the chemical properties of two specific carbon compounds we mentioned earlier, ethanol and ethanoic acid. Ethanol, also known as ethyl alcohol, is a volatile, flammable, colorless liquid. It's a versatile solvent capable of dissolving both polar and non-polar substances, which makes it invaluable in a variety of industries. It's also a key ingredient in alcoholic beverages thanks to its ability to undergo fermentation. Now onto ethanoic acid. Also known as acetic acid, it's a weak acid that gives vinegar its characteristic sour taste. But that's not all it's good for. It also finds use in the production of various chemicals and plastics. But what happens when these two compounds react with each other? Well, they undergo a type of reaction called esterification to form an ester, in this case, ethyl acetate, which is used in nail polish removers, glues, and also in the wine industry to improve flavor. So, as you see, ethanol and ethanoic acid, though simple, have a wide range of applications due to their chemical properties. Having explored the chemical properties of ethanol and ethanoic acid, let's now dive into an example of an addition reaction, the hydrogenation of vegetable oil. Addition reactions are those where atoms or groups are added to unsaturated organic compounds. In the context of our discussion, hydrogenation is a specific type of addition reaction. But what exactly happens during hydrogenation of vegetable oil? Well, it's the process of adding hydrogen to unsaturated vegetable oils to make them more saturated and solid at room temperature. This is a common practice in the food industry, especially in the production of margarine. So, the next time you enjoy a sandwich with margarine, remember, chemistry is at work. Through hydrogenation, we can transform liquid vegetable oils into solid fats, demonstrating the practical applications of addition reactions in our everyday lives.